Hello, everyone. So this is another MATHCOUNTS problem. So this was a state run sprint number 25. Okay. So we have a 2x2 grid that is shaded. And then starting from the top left corner of that 2x2 square shaded figure, we start writing integers on a clockwise 1, 2, 3, all the way to the 18. And if I want to continue this writing those numbers, what will be the integer on the in this 6 squared to the right of the squared number 5? Okay, so this is the first, and this guy will be the second, and this is gonna be third. That's fourth. That's fifth, and this is gonna be the last one. So this is what we want to find out. Okay, so if you have no idea, on a sprint run, like you can maybe go ahead and list all the integers, like counting, maybe not writing everything, but it will take a bit longer, but it will give you anyway the answer. So that's something you can try, but I'll try 2 different ways. But those 2 ways will be somehow same, especially for the first part. Okay, but the ending part will be a little bit different from each other. So what I'm gonna do, I'm gonna list a bit more. So that's 19, that's 20, 21, 22. To make a bit better looking, so actually I'm gonna make more squares, right? So that is one of them. So 22, so 23, 24, 5, 6, 27, 28, 9. Okay, let me see. 29, 30, 31, 32, 33, 34, 5, 6, 7, 8, 9. That's 40, 41, 42, 43, 44, and 45. Okay, this is something I have at least for now. As you see, to save like time, I just skip some of the numbers in the middle, which is okay to do so as long as you are really careful with counting. So I can continue with a bit more, which is okay, but I will see if I have some easy way to go from here, okay? So, we are talking about these squares, which is like 2x2, 3x3, 4x4. If you have like 2x2, you should have 4 numbers in that 2x2 squares. If you have 5x5, you have 25 squares. But at the same time, the 4 like original squares are missing numbers. We just need to have 4 lesser than a perfect square. So like what I mean by basically, let me actually show some example. Since I need to start with at least 1, 2, 3, I will just go with 3x3 square. So if I take this 3x3 square, I do need 9 numbers if I write numbers on inside of each of those square, but I do have no numbers on these 4, so which is 9 minus actually 4 will be 5. And we are given that 5 is actually as the number in this corner. So I can write as like 3 square, which is the number of numbers in that 3x3, and minus 4, which is gonna be 5, which is actually the last number that we have written in this 3x3. And if I wanna kind of do the same thing, okay, with the maybe 4x4 or 5x4, but I'm gonna take this guy first. Let me do that. So if I take this by now, which is like 5x5, and I do have 5 squared, which is 25 numbers in that, I should have 25 numbers, but the 4 is missing. So I should subtract that, which is 21. I do need to have 21 numbers. As you see, 21 is actually in this corner, which is actually adjacent to the other number that we received. And if I want to continue the same thing, the next number should be 7 squared minus 4, which is 49 minus that will be 45, which is really nice. That is right there. So as you see, these are the odd perfect square, not the even ones. Why this is the case? Because, okay, if you take the 4 square, which is like 4x4, that's 16 minus 4 is 12. That is actually right here. So if you really want to make a 4x4, including 1, 2, 3s, so you should have something like this. Okay, and then if you want to do 6x6, you should have something like this. based on the pattern that we start listing. So that is gonna be 36 minus 4, which is gonna be here. So this is 4 squared minus 2. This is 6 squared minus 2. And the next number right here will be 8 squared minus 2. But since we don't really care about the numbers in this corner, we just need to know this region. So I just like to work with odd powers in our example. So now, as soon as we see this pattern, okay, then I can just keep finding the other missing numbers that we have. So my next number could be, 9 squared minus 4, which is gonna be 77. So that means the number right here is 77. And if I wanna do this 11 squared minus 4, which is gonna be 117, so that will be right here. And if I wanna do the 13 squared minus 4, which is 169, minus 4, 165. So my next number will be right here, which is 165. And the last number is 15 squared minus 4, which is 221. And which is gonna be in this square. But this is not what we want. We want is this number. So you can just like go back because the numbers were increasing by when you go top to bottom, 18, 19. So this is 221, so that should be 220, and that's 219, and that's 218, right? Actually, yeah, 218, and that would be 217. Okay, so this is this row, this is this row, this is row 445, and we have one more, so 216, and this number will be 215. And that is my number. So this is one way you can actually do this problem without really adding too many numbers. But if you didn't really see this approach, which is okay, we have something similar to this one, a bit different, but I'm gonna ignore this right now because I'm gonna assuming that I have no idea about the first approach. Okay, this was the first one you could have done, but let's say we don't see this immediately, okay? And I'm gonna find something else. Actually, let me put this back. Let's see if that's the case as our second approach. The second approach that I'm gonna try is I'm gonna focus on the numbers on this row because these are the numbers I need to know at least. So I start with 5, and then I have 20, I have 43 so far. And if I want to find the difference between these integers, which is going to be 15. And if I want to find the difference between these two integers, that will be 23. I'm not sure if you know about this approach. When you find the difference between these guys, if the numbers are equal, and then we are going to call this is going to be linear relation. But if you have a numbers that is not, okay, 46, 47, 48, 49, that will be 50, 51, 52, 53, this corner, 4, 5, 6, 7, 8, 9, that will be 60, 61, 2, 3, 4, 5, 6, 7, 8, 9, that will be 70, 1, 2, 3, and 4. So, okay, I think that's 74. So let me write that. So now if I want to find the difference between these two guys, 43 to 74. So 43 to 73 is just 30 plus 1 is 31. And now I have these three numbers. Let's take another difference. So difference between these is 8. Difference between these two is really nice, which is 8 also. So now I do have the difference are the same. So which means this pattern will continue. So to get this 8, like the difference between the 31 and the next integer to be 8, so this has to be 39. So, and then this 39 is difference between this number and the next number. So 39 plus this will be 113, right? So because 113 minus this will be this, or you can add this guy to this to get this number, which is what I just did. And now if I want to find the difference between the next two, so the difference between this and this has to be 8 as well. So let me write this. So 8 plus this number will be 47. And now this guy plus this guy will be this minus this will be that, right? So 47 plus this 113, which is nice, which is gonna be 160. And I will just do one more, right? So that should be difference between this guy and this guy should be 8 again. So that will be 55. And this guy is difference between this by them, or if you add these two, you should be getting the next integer in your list. So 55 plus this will be 215. And as you see, this guy was actually the number that we got. So this is the first number, which is 5. And this is my first, second, third, fourth, fifth, and the sixth number. So again, this is something some people may know, like if you know about the Fermat's-Lewis theorem, this is something you actually do when you use that, but we don't really use that Fermat's-Lewis theorem in this case, to be honest, but we are just using the approach that is actually used in that theorem, okay? But that is basically what you can do.